Last time we had looked at the first half of this 10.4, which is essentially adding and subtracting. We have to break down the radicals by taking out a perfect square, and most of the time you're going to end up with a common radical that you can add and subtract for like terms. So now we're going to deal with multiplication, which I think is generally easier for the most part. There's slightly a different rule for this when you're talking about multiplication of variables versus multiplication of radicals. Multiplication of variables, remember when we had like bases, we add the exponents. Well, here, what we do when we multiply is when we have, hello, Trinice, can you hear me okay?
We can hear you fine.
Okay, good. So what we do when we multiply radicals is we multiply, if there's no number in front of the radical, we multiply just the one radical times the radical. In other words, whether the square root of 3 is going to multiply the square root of 3, and square root of 3 is going to multiply the square root of 6. The number in front of the one in the binomial, those are going to stay there, but they don't get multiplied unless there's a number in front of the value we're multiplying by. So on this one, they show us with the little arrows, the square root of 3 is going to multiply the 2 square roots of 3. Square root of 3 times square root of 3 is square root of 9. You multiply what's inside one radical times what's inside the other radical just by basic math, and then you're going to simplify that if possible. And then square root of 3 times 3 square roots of 6. All right. So 3 square root of 2, square root of 3 times 2 square roots of 3 is 2 square roots of 9. The 9 is going to turn into 3. We'll see what happens in a second. Square root of 3 times 3 square roots of 6 is 3 square roots of 18. All right. And then 9 times 2 is how 18 is broken down. As long as a perfect square in there, we're going to take it out. Square root of 9 times the square root of 2. Square root of 9 is 3, and that multiplies. Until it comes out of that radical, it does not affect the number in front. So the square root of 3 times square root of 3 is 9, and then the square root of 2 follows along with it. And there we got 6 minus 9 square root of 2. All right, any questions about how that works? All right, the first row is not going to be nearly as advanced as that because we're just going to be multiplying one term times another term. All right. So what we've got here on this one square root of 2, 10 times square root of 2. What do we end up with there? You can put in an intermediate step if you like. Because remember, we've been breaking these apart because that's one of the rules of radicals is the multiplication rule. That if we have things that we can break apart factor-wise inside of a radical, we can then break that into two different radicals and then simplify as needed. But here, we can kind of go back the other way and put them together. So that's going to be square root of 2 times 10. which is square root of 20. Is that finished? We got to go back to what we learned in 7.3 because that's where we first started looking at simplifying.
4 times 5.
Yeah, that's 4 times 5.
So it'll be 2 is square root of 5.
Exactly. So that's 4, I'm sorry, times 4 times 5. I messed it up. What am I doing that for? There we go. 5 times 4. 4 times 5. And then the square root of 4 is 2. And the square root of 5 stays inside. Looks good?
Yeah. Professor,
Mm-hmm.
can we go back to the example real quick? Why do we now subtract the 6 from the 9?
Because there's a negative sign in between here. This one's positive, and this one is a positive times a negative, so this one stays negative. Why do we not, you're asking?
Yeah.
Because this is 9 square roots of 2. It's not 9. This is 6, but that's not 9. That's 9 square roots of 2. So
Okay.
if you were to look at it, square root of 2,
Looking at it as a whole, not just one. Okay.
okay, so times 9. So that value is actually, just as an approximation, is 12.72. It's not 9. It's 9 times the square root of 2, which is approximately 12, almost 12.73. But they're not the same thing. This is 6 wholes, and this is 9 square roots of 2. Sort of like, it works on the same basic principle as the variables do. Remember, if you got 6 minus 9x, you can't put those together because one of them is whole numbers, the other one are x's. They're different terms, like apples and oranges or something like that you could think of. All right. So on this one, all right, we're going to do those and these. There's 2 multiplications. See, this is the numbers are going to multiply times one another. And again, this is just like variables. If you got 2x and 3y, you can multiply the numbers, and then the x's and the y's stick together, but they don't change. Now, these are going to change here in a second because this is where the variables are different from the radicals. The radicals multiply inside just like regular numbers. So it's a little bit different than from variables, because with variables, remember, we had the rule to where they're like bases, then we can add the exponents. So this is 2 times 3, and then square root of 8 times square root of 10. So this is 6 square roots of 80. All right. Now, if we have something that we can multiply, I'm sorry, if we have a perfect square inside of there, we can break it apart and make it simpler. Now, one of the things we could have done on 2 square roots to 8, we could have broken that down first if we'd wanted to, because the numbers will get big pretty quickly in some cases when you don't do this, but this could end up being 2 times 2 square roots of 2, which is 4 square roots of 2. So if you wanted to, you could do that first. But with this one, I don't think it's that large of a number, because square root of 80 is 16 times 5, right? And then the square root of 16 is 4. And the square root of 5 stays in there. So this is 24 square roots of 5. Okay?
Yeah.
All right, and then the same rules apply. I mean, if you're multiplying 2 times 3 times 5, generally you just multiply any two together and then multiply them times the third. All right, so we're going to do the same thing here. We're going to have the 2
Hey, babe.
All right, so I just kind of lined them differently so that we have the whole numbers together and the radicals together. So then this is 2 times 3 is negative 6, times 5 is negative 30. And on the inside, we got 2 times 3 is 6, times 6. Anything we can simplify there?
For the 36, you can break it down 6 times 6.
Mm-hmm.
So that end up being 30 times 6. Negative.
And that's 180 negative. Okay? All right. Any questions about that one? All right. Now we're going to be dealing with here a monomial times a binomial, but it's pretty much going to work the same way. We're just going to multiply this times this and that times that. Since there's no number in front of the square root over here on the left, then there's nothing to multiply the 2 and the negative 4 by. So 5 times 15 is square root of 75. And then this is negative 4 square roots of 45. Correct?
Yeah, that's what I got.
What can we do now? Can we do anything else with these things?
And you can break down 75 as in 25 times 3.
Yes, that's exactly right. Now you got to watch here because this is not like ones you've seen before where they're going to end up having that same. So, for example, if you tried to take the 3 into the 45, you're going to get 15, which is not a perfect square. So we got to think a little bit differently. And this is where it does help to have some multiplication table experience, because that's 9 times 5 in there. All right. So square root of 25 is 5. And then the square root of 3 stays in there. Well, I'll tell you what, this is 3, because the square root of 9 is 3, and then the square root of 5 stays in there. And you know what? See, look. 10 square roots of 3 minus 12 square roots of 5. They are not alike, so you do not want to put these together if you're ever in a situation like this. They have to be the exact same. I think that's called the radicand. The index is the number in the crook, and the number inside of the radical is the radicand, and both of those things have to be alike. All right, now the FOIL method is going to work on most all of these here, but there are certain ones that follow a specific pattern because we have the sum of squares here and what we call the difference of squares, and we can use that shortcut formula if we wish. But for all of these, 1, 2, 3, 4, 5, we can use the FOIL method. Some of these can be quite long if you use the FOIL method, which is why I'm going to show you on certain ones a little shortcut. So this is 2 square roots of 2 times square root of 2. That's your first. Outside is positive times positive. Positive times negative is negative. Then it's 2 square roots of 2 times square roots of 6. And like I said, I'm going to run out of room here. Negative times positive is negative square root of 36. All right, so that's outside, inside, and the last. So this is square root of 2 times square root of 2, so that's square root of 4, which is going to end up being 2. This is square root of 12. And then this one's also going to have a square root of 12 there. And then this is just going to be 6. All right, so that's 4. And then this is 2 square roots of 3. And then this is going to be the same thing, except it's going to multiply. So 4 minus 6, I'm going to put them together. And then this is 2 square root of 3 minus 4 square root of 3. Minus 4 square root of 3. I said it and then I didn't write it. So this is negative 2 and 2 minus 4. All right, how does that look?
That's not good.
It's a long one. That's why I'm going to bring your attention to what we looked at in the last part of chapter 5. This will make it shorter. All right, so this is going to be square root of x. So it's this times this, and that's going to be negative. And then this is always going to be positive because it's negative 3. Negative times negative. It would be a 3 squared. So that's the square root. Anytime we square a square root, the inside just pops out. And you see how that's a lot shorter. You can go through the foil. Like I said, just sort of how you did with this one. And with the 14, we didn't have much choice. But that's the formula for what we call the sum of squares. Okay, questions? All right, now this one's called the difference of squares. This is the one that goes like this: x minus y times x plus y. Notice that the only difference is just the negative sign in between the two. So this ends up being x squared minus y squared. All right. So, pour it out if you'd like. But like I said, you're going to lose the middle terms. Square root of 2 squared is 2. 7 squared is 49. There's a negative in between the two. 2 take away 49 is 47. All right, questions about that one? All right, now this is another one. It's like this one. It's different in that the first term also has a coefficient in front, but we can still do the same thing. We can go so it's going to be 2 of them. That's what that 2 is for. And then it's negative 3 times negative. I'm sorry, negative 3 times positive 3. Is 9. And then plus. So when we square this, we square the number in front. which is 9, and then we square this, which is just going to be 2, but I'm going to put square root of 4. Oops, I'm sorry, this is, doesn't have a sign on it. I already got the negative sign there. Because it's going to be that same sign there. Oops, 9. And then this is 2. Square root of 4 is 2. It's 18 plus 9. Those are going to go together. And then you got negative 18 square root of 2. 9 and 18 is 27. All right. All right, any questions so far? We got plenty of time, so I'm going to have to come up with some more problems here to give y'all to work. Let's see. So that next one, I mean, there's only one choice. You just got to fold it out. They're not the difference of squares or the sum of squares. So what happens with that one? So, so what we're doing here is we're multiplying this one, that one. So that's the first, the outside, the inside, and the last.
I've got an answer.
All right, let me go through and work it. Anybody else got one? All right, so this is going to be, it's going to take a lot of room because, like I said, this is time, space intensive, I guess you could say. Positive times a negative, so positive, a negative times positive, so it's another negative. Negative times positive. All right, so this is 3 times 4 is 12. Square root of 3 times square root of 3 is square root of 9, which is going to be 3. So this is 3 times 2, which is 6, and it's negative. Hold on a second. Okay, yeah, it's totally different ones, I guess. So I thought it was the same. So 3 times 6 is 18. This one's also negative. It's there's only one coefficient. All right. In actuality, I could have just added these here and then only done this one time. But now that I've already started. I'll simplify that in a minute. So these two are going to go, so that's 48, 36, and 12. Okay, and that's square root of 9 is 3. And then square root of 2.
Okay,
All right.
that's
So that's good?
yeah.
Yeah, again, this is kind of long and drawn out, but whew. All right, that's all the ones on here. I'm going to give you all some to work there. What's going on? Why is this so slow? All right, work that one. See if I can find another few. one more. All right, give those a try. I'm gonna give you a few minutes. All right, let me know when you get something on this. Well, on the first one. All right, what happens on that first one?
Okay, I multiplied them, so it ends up being square root of 33 plus square root of 22. I haven't broken them down though. I don't know.
Well, let's see if we can break them down. I don't think these are because they're both the only factors are going to be 3 and 11, right? And
Yeah,
3 and
that's what I'm
20.
saying. So I think that's the final.
Yeah, this is all right. Try the next one. So you can fill this one out, and I'll do that this time. Using that formula will give you the same result. All right, is that look good? We're not finished yet, but that's doing the foiling part.
Yeah, that's what I got.
All right, so let's go ahead and just finish it. So square root of 49 is 7,
Yeah.
and this is negative 1 and negative 1. That's negative 2. Square root is 70. I don't think that's going to simplify out any. 7 and 100 is 107.
Wait, how
All right.
the for the 100, wouldn't that be square root 10? Well,
Oh, that's what I meant to write. I was just, you're right. There. I mean, yeah. So it's 17. Yeah. I don't know what I was thinking. Square root of 100 is 10, and then 10 and 7 is 17. And you can look, I mean, 70, let's just see if there's something that'll, because I don't think there's 4 that'll go into it. No, let's see. And then 70 doesn't divide by 9. And 70 is not divisible by 49. So that's it. All right, try next one. This one. All right, what happens on, say, first? Somebody let me know when y'all getting close on it.
I got an answer for it.
All right, so let me go ahead and see. So 5 square root of 3 times square root of 3. Outside is 5 times 2. And square root of 3 times square root of 5. Inside 2 times 2. And then that's square root of 5. Square root of 5. So this is 5 times square root of 9, which is 3. And then this is 10 square root of 15. And then this one is 2 square root of 15. And these are all positive. Plus, which This is going to be 5. Okay. Whew. And this is 10 and 2, which is 12. And that's a 5. So that's 20. All right.
That's what I got.
Okay, good. Now the next one can be easier or hard, depending on how you do it. If you fill it out, it might take a little bit longer, but notice that that's what, then we're going to learn this term in the next section, the conjugates of one another. In other words, they're the exact same terms except for the negative sign in the middle. All right, does that look right?
Yeah.
All right, let's try to do a couple more before the break. See how that one works out. All right. What's going on with number 5?
Professor Cruz, just to verify that second part of the problem, is that 8 square root x?
Yes, it is.
Okay.
8 square root of x. And that's also, like I said, is when you multiply sometimes itself, it's squared. And that's going to be important in the next section. So squaring of a radical takes the insides out. So we're going to learn about that, how that report is important next time. So square root of x squared is just x.
Minus 56x. Square root
Yeah,
x.
minus 56. Square root of x plus 63. Those two are the same. Now, important, an important, how would you say this, aspect of this, and you'll kind of see it when we get it all. Well, that's 92. 92 square root of x. We've got three separate terms there. There's no x squared term. So that's because when you multiply a square root times a square root, you just, a square root of x times a square root of x, you just get an x rather than an x squared. And so this one in the middle is just 92 negative square roots of x. This is kind of like a quadratic in that, you know, in the quadratic chapter, where did I get? Was it 6 when we were factoring those? Well, you also multiply and get them when we're in chapter 5, but you had x squared and then x, and then you had a number. Well, this kind of follows a similar pattern. It's just a bit different as far as that, that the highest power is just plain old x.
Well, the last one I got -4.
All right, let's see now. I'm going to take the shortcut here. Now, also when we come back, this is going to be an important tool. These are what we call conjugates of one another. Remember, they were called difference of squares in chapter 5 when you're dealing with and without radicals. But when you got radicals, they call them conjugates because they're opposites. They're the same in every aspect except for the sign in the middle. And you know what happens when you multiply something by its conjugate? You lose your middle terms. And so there's only the two n terms squared with a negative in the middle. So it's -4. All right, so let's take a little break and then we'll come back. I'm going to have to go walk around. I'm tired. I've been up since real early this morning. So, and then when we come back, we'll look at this next section. And I'm going to go ahead and put it up here. It's called Rationalizing the Denominator. And we're going to use that, at least over here in the second part, we're going to use that conjugate idea. But I'm going to leave that there. And then the process by which we do away with of a radical in the denominator is to use that principle of squaring a radical. In other words, if we multiply a radical by itself, same term by itself, then poof, there's no more radical. So watch what I'm talking about. This isn't the best example, but it's a more advanced example than the ones they have in here, the first two. But nevertheless, we can follow it. Now, remember, we can break this radical apart with a fraction underneath it by having a fraction in the numerator and the fraction in the denominator. So square root of 5 over the square root of 18. Now, we could go ahead at this point and multiply numerator and denominator by the square root of 18. But we would have something pretty messy because 18 times 18 is a pretty big number, and then we would have to break that down accordingly. So the best thing to do, if it's not already broken down like the square root of 18, is to go ahead and do that first. Square root of 18 is the square root of 9 times 2. So that means square root of 5 over the square root of 9 times the square root of 2. The square root of 9 breaks down into 3, and we still get a square root of 2 down there. Now that's a lot smaller number to multiply by than multiplying by the square root of 18. Because 18 times 18, some huge number, I couldn't even tell you what that is right now, but it really doesn't matter because we've got an easier way to do it. Now they show this right here that we're going to multiply by 1, and what they mean by that is if we multiply any fraction by a term over itself, like square root of 2 over square root of 2, that's the equivalent of 1. And it does not change the value of that expression. So, in the numerator, it's square root of 5 times square root of 2, which is square root of 10. Down here, it's 3 times square root of 2 times square root of 2, which is square root of 4. And the square root of 4 is 2. 3 times 2 is 6. And there we've got an expression that's equivalent. Let's see if I can show you what I mean with the calculator. All right, so square root of 5 divided by 18 is equal to 0.57. Now I'm going to go here and jump down to our final expression that we simplified. And if that was done correctly, see that? Those two things are equivalent. Now, this is the exact value. These right here, when we take it and write it down as a decimal, it's an approximation, so it's not as accurate as this. And the reason being is that in computing and such, if you need to be very accurate, the computer's got the ability to store this into the hundreds of decimal places, therefore making calculations very exact. So anything that we would do to round this off is going to just approximate it, and it won't be nearly as accurate as it is here. But that just is an exercise to simply show us that these two things are equal. All right, does that make sense? All right, so on this first one, tell me, what would I multiply both numerator and denominator by?
7.
Square root of 7. And square root of 7 over square root of 7. This right here is equal to 1. So we're not changing the overall value of this. We're just putting it in a different form. So up here, it's 3 times the square root of 7. And down here, it's square root of 49. Because essentially what we're doing when we're multiplying these two is just square root of 7 times square root of 7 is equal to square root of 7 squared. And when we square a square root, it just merely gets the inside out. But that's the same thing that's going to happen here. All right? It's simply when you square something, in other words, multiply by itself, the insides just come out of that root. So let's see, square root of 7, let's say 3 0.13, so that's that one. And then if we go up to the top and do the original one, see, they're the exact same value. So, all right, questions? Why don't you go ahead and try the number 2, and just remember, you break it down like this first. So what's that form going to take on when you rationalize the denominator?
Square root of 10 over 5.
What is it?
Square root of 10 over 5.
Square root of 10, yep, over 5. Like I said, you don't necessarily have to put all of these steps in there, because the idea is just to put in the steps that you need in order to do it yourself. But I try to put in as many as I can, at least for the first few times that I do something. So the reason why it's called rationalizing the denominator is because there is no longer a radical in the denominator. All right. So try the next one. I'm curious to see kind of how you do it. Not just the final answer, but I'd like to kind of know what you're multiplying by. The reason why I'm asking that is because there's a couple of different ways to handle this one.
Okay, I made it to a certain step, and I'm just not sure if it can be simplified more.
Okay, one of the things that may make it easier, I would probably be tempted to just multiply like this, because 8 is not that large,
Hmm.
all right? But you could also go ahead and instead write this as 2 square roots of 2, because it's the square root of 8 is equal to 4 square roots of 2, and then the 2 comes out, and then your x stays in there. You could handle it either way, and then multiply by square root of 2x. All right, so let's just kind of see how, if they come out any different, or if they come out the same. So this is 3 square root of 8x. And then this is going to be square root of 64x squared. And then this is going to be 3 square root of 8x over 8x. All right. Now, problem is because we didn't simplify the 8x like I did here, we're going to have to do it here anyway, but it doesn't really matter. All right. So what ends up coming out here is a 2. So that's 3 times 2 square roots of 2x over 8x, which is 6 square roots of 2x over 8. Now let me go ahead and finish this one down here.
Okay, that's where I stopped at. So that can't be simplified more, right?
Well, this one can, and that's what I was going to show you over here. All right. This is 3 square root of 2x, and then this is 2 times 2x. Oh, wait a minute. There was an x down here. I'm sorry. I forgot about it. All right. Now, there's no simplification between 3 and 4, but what about 6 and 8? 3 goes into there. I'm sorry, 2 goes into there 3 times, and it goes into there 4. So in either case, you're going to have 3 square roots of 2x over 4x. At some point, you have to simplify that square root of 8x. So whichever you think is easier, I think this one may well be easier, but I probably would have started there just because, when I'm doing math, I just take the first thing that pops into my head, even though it may not necessarily be the shortest way. Sometimes I do that, but sometimes not. So both of these are essentially the same thing. All right. So last one, and like I said, with this one, I would highly suggest breaking that down as 4 times 5 first. Because with the 8x, even though the 8 could be broken down, 8 times 8 is not that large. 64. Square root of 4 comes out as 2. All right. Now notice here, we can do some simplification. All right. 2 goes into 2 once and into there twice. So what you've got is 2 over square root of 5x. Now, it's still not rationalized, but that one is a lot more like probably the first one, because there's, you only need multiply now by square root of 5x. And anytime you multiply something by itself or square it, it just pops out. All right, does that make sense? Does that look good? Did I do it right?
I'm not sure. I think I always suck at the shortcuts. I think I'm good at the long way.
Well, but what would the long way be? You're going to use the big number?
Yeah, I don't know why. Is whenever I do shortcuts, I always end with the
But
wrong
I
answer.
mean, it's not, I don't know if that's necessarily shorter. I'm just saying is you simplify it first. So let's just see.
I'm doing something wrong.
4 square roots. All right. So the whole thing's underneath there. So this is 4 square roots of 20x. And then what is 20 times 20? That's like 400, right?
Yeah.
Okay. Now, well, we don't have any choice now but to simplify both of these. Okay. So in the top, it's not so bad. So what's the largest perfect square in 400?
A long way is the long way.
I'd have trouble thinking about it now. Let's see. You got 100 times 4, but it's really just 20x, right? So because it's x squared. So just what I was saying is, anytime you multiply anything by itself, you just get what's inside out originally. So now that's 4, and this comes out as a 2. Doesn't hurt to do it more than one way if you're not sure. So this is 8 square roots of 5x over 20x. And then we can just look for a common factors in between here, which it looks like it's 4, right? 4 goes into there twice and into there 5 times. So there we got it. See that? Exactly the same.
Figure out why I went
So
wrong.
I would just, I mean, like I said, it's the way that I like to tout doing
Yeah, I
math
don't
is just
know.
go with your instincts
Yeah, I just don't know where I
because
went wrong
that's
first.
the best way. You don't want to do something you don't know how to do. So, but one thing I would just suggest though is for something like that is break it down first. That's all I would say if you can possibly manage that. But it still comes out the same way either way. All right, let me find a couple more to do. And then we'll go on to the last set. The last set doesn't have that many. So let's call this one number 1. All right, I'll give you all a chance to work on them. If you break that down first, then it's gonna generally make it a little bit easier. I mean, you can still multiply square root of 9x times square root of 9x and then get 9x. It's not gonna hurt. But look what we also happens here when you do this. Look at this. 3 goes into 3 one time and into there once. So now we've got 1 over square root of x. It's a lot easier to do. So what do we get? Is that right?
Yeah, that's what I got.
Okay, good. Try that next one.
I got 4 square root of x over x.
All right, you got it? Okay. Let me get over there and mess with that. So this can be broken down into 4 over square root of x. And then we're going to multiply top and bottom by square root of x. Same thing we did over here. All right. All right.
Yeah, that's what I got.
Okay, dokie. Let's look at the last type. Now, as I had said, let's see here. That's terrible. Terrible X. So what does that mean? That means if we start out with square root of x plus 2, its conjugate is square root of x minus 2. But if we were to start out with square root of x minus 2, its conjugate would be square root of x plus 2. So that's why they call these things conjugates. And the reason being is they're exactly the same except for that plus or minus. So there's just that one small difference in them. They're exactly the same except for that. All right, so let's we'll come back over here if we get some more room. But we're going to go on to here now. No, it was on the bottom down here. That's right. All right. So, of course, they're going to give us a hard one as an example because it does a little bit of everything. But I'll make your way through it, and then you'll see the ones like the first one. Neither one of these as hard as the example. And I'm going to get you one that'll be on the same level with this. All right, so 2 over 2 square roots of 2 plus 3. We want to rationalize the denominator, so we're going to take advantage of those conjugal relationship between those two. All right, so what it means we have to do is multiply by these same terms except for the sign in between. All right, so that means 2 square roots of 2 plus 3 times 2 square roots of 2 minus 3. And like I said, what happens is you end up, when you go through all the 4, and that's fine if you do that. But we're doing this property here, this principle from chapter 5. And that's why I had stressed it in multiplication in 7.4. It makes this a whole lot easier if you can pick it up. You're going to lose those middle terms because since the only thing that's different is the negative positive, then the two middle terms, poof, they're gone. They take each other out. Those truly do cancel one another. People talk about, this over here, or this cancels one another. They don't really cancel each other out. It turns to 1 because everything is divided by 1. But when you multiply these two things, you're going to have those two opposite terms. One's positive and one's negative. Bam. Those are truly 0 now. They're not even in their expression anymore. So up here is the important part. So it's square root of 2. Wait a second. They made a mistake here. That should be a square root of 2 there. I didn't make this, though. This is not my mistake. Y'all know I don't ever make mistakes. Anyway. All right, so square root of 2 times 2 square roots of 2 is 2 times square root of 4, and square root of 2 times negative square root of 3 is negative square root of 6. And then down here, Like I said, we're using that formula. It's 2 square root of 2 squared minus square root of 3 squared. 2 squared and square root of 2 squared is really what's happening. Remember, we're just squaring both of those. That's 4 times 2. And that's why they have that there, and then it turns to 8. So up in the top, it was 2 times square root of 4 or 2 times 2 minus square root of 6. We don't care if there's a square root in the numerator. So 4 minus square root of 6, 8 minus 3 is 5. That's all there is to it. So,
I see we back to doing paragraphs for word problems now.
well, all right. So try. Well, that's the good thing is I don't think there are any word problems in this section in this chapter.
I'm just saying these problems get longer and longer.
Well, yeah. I mean, but that's always what happens. It always starts out with little things, and then you put all the principles together. And but I don't think there are any word problems in here. Now there may be word problems in chapter 11, but not in chapter 10, because we do equations, and then these are complex numbers. Okay, and then I think there may be, I don't know, there may be some applications here. I don't think so, but it shouldn't be bad. If you've never used the quadratic formula before, that's a whole lot easier than factoring. As a matter of fact, that got me through most of my undergraduate coursework was using the quadratic formula rather than factoring. But anyway, let's see, over here, right? So first of all, just tell me, what's the conjugate? In other words, what are we multiplying by?
Square root of 7 minus 2.
Yes. Square root of 7, not 2. Can't make a good 7 for anything. All right, so try it. I'm going to try to find a good third one. Oh, let's try that. Okay. I was trying to find one specific type that might be useful in chapter 11, and I was just able to find one. They don't have any in the homework, and even online is because one of the things that when you do this, I'll show you what I'm talking about. All right, here's a good one. Try the last one. All right, so let's just see what happens on this. So it's 2 square roots of 7 minus 4, because it's 2 times 2, negative. And then this is just square root of 7 squared minus 2 squared. All right, now
Okay, that's what I got.
if this 3 divides into both of the values there, you can simplify further. Okay, but this doesn't, so the one that I'm going to get for you is going to illustrate that. All right. So that's 3 square roots of 7 minus square root of 77. And then this is 3 squared minus square root of 11 squared, which is just going to be 11 coming out. So that's 3 square roots of 7 minus square root of 77. That can't be simplified. The only factors of 77 are 11 and 7, right? So neither one of those are perfect squares. And again, not the 2, it doesn't go into 3 or 1 up there, so we can't. Hopefully that's right. I did it quick, but because I wanted to show you one. All right. I'm going to put it up here so we got plenty of room. I don't know if it'll take all the room, but it's got to have some breathing room. All right. See what you can do. Then I'll come through and okay. So 6 times 3 is 18. And this is 3 squared minus. So that's 9 minus 7 over 2. Is that all we need to do on that one? Remember, we've always got to simplify things down as far as we can.
18 times 2, correct?
All right, let me just show you something. All right, I want to put it back the way this was up here. It's 6 times 3 minus square root of 7. And this just might make it a little bit more clear. See, these are multiplying, so 6 is a factor of both of those. And then down here, you just get a 2. Well, 2 goes into 2 one time, and then 6 3 times. So all you're left with is 3 times 3 minus square root of 7. No longer is there a denominator. So you can simplify using whatever value is in the numerator, provided it divides into both of them. Okay? That's why, like on this, well, this was a bad example because 3 didn't divide into either one. But if this had been a 3 and this still been a 4, you can't, if the 3 is not a factor of the whole numerator because those are separate terms. So just keep that in mind. And even if you don't have any homework problems like that, I think it'll help matters in chapter 11. Okay? Any last words? All right, so Wednesday, on Wednesday, I'm just going to give you a highlight of what Wednesday's about. Just jump into some other mode. But we're going to take advantage of that fact that if we square something, in other words, if you have the square root of 2, and you square it, then the 2 pops out. So with a radical equation, just look at this example. First of all, you don't want to do this if you've got other things besides the radical over there. So in this case, there's a negative 8. So the first thing we got to do is add 8 to both sides so that the 3x minus 2 square root is by itself. And at that point, you square that, and you also have to square the right side, doing the same thing both sides. So this just pops out, 3x minus 2 is equal to 49, 7 squared. And then you solve it, just like a regular linear equation. Now, here's the thing we got to remember. When we square both sides, there is a possibility that all of the solutions won't be bona fide solutions to that original equation. So we have to check them. This one works fine. 17 fixes it. But you're going to find out, and I kind of can, since I'm a prognosticator here, we're not going to do these today, but I'm going to be betting that this one is going to lose a solution. Anyway, that's enough. I'll see you guys on Wednesday. So have a nice couple of days. Make sure you keep up with your work because, like I said, it's this time next week. We are testing on chapter 10 and 11. And then 2 weeks from tomorrow, this next class is our exam. Essentially, our exam will be pretty much over with. Because next week's our last full week of class. Then we got a half a week, just Monday. And then the exam period starts. All right.
All right, you have a good night.
Bye-bye.
All right, good night. Bye-bye.
Night. See you later, Trinice.
All right, Mr. Cruz, have a good one.